Hi dear students, last class we discussed about internal energy, work, etc. Today we are going to discuss about another thermodynamic property, that is enthalpy, represented by H. So today we are going to discuss about enthalpy represented by capital H. Now what is enthalpy? Enthalpy is defined as the total heat content of a system. Enthalpy is the total heat content of a system. So I am going to discuss, or I am going to explain about enthalpy with some examples. Please listen carefully. Consider a cylinder filled with water or filled with a gas, HCl gas. Okay. Years ago, we thought that all the process in the universe occurs at constant volume. All the process. Years ago, we thought that all the process occurs in the universe. All the process in the universe occurs at constant or take place at constant volume. All the process in the universe take place at constant volume. That means delta V is equal to 0. Okay. Years back, we thought that all the process in the universe occurs or take place at constant volume. That means delta V is equal to 0. It means that when you heat water in a vessel, okay, volume of the water remains same. There is no change in volume. That means before heating and after heating, volume of the water remains same. Because earlier concept was all the process in the universe occurs at constant volume. That means delta V, change in volume, is 0. So when you heat water taken in a vessel, before heating and after heating, volume of the water remains same because volume remains constant. But we know that this is not true. Because when you heat water, water will evaporate to form water vapor. Obviously the volume will decrease, right? So there is a change in volume. That means earlier concept was wrong. Right? Earlier concept was wrong. Now, according to earlier concept, according to previous concept, all the process in the universe occurs at constant volume. This means work, pressure, volume change, that is work, W is equal to minus P external delta V. Here's external pressure is equal, volume is equal to delta V is equal to 0. So that you will get 0 into minus P external 0. So when you heat or when you do some chemical reaction, work always remains constant. But it is not true. In last topics we learned that there are two types of works. If work is constant, then why we learn two types of works, right? So this concept was wrong. All the process in the universe is not taking place at a constant volume. Okay. If it take place at constant volume, then for all the process, work will be equal to 0. Minus P external into delta V. Delta V, change in volume 0. So W will be equal to 0. Okay. If W is equal to 0, according to first law, delta U is equal to Q plus W. If W is equal to 0, delta U is equal to Q or QV, heat at constant pressure. This means when you heat water, according to old concept, when you heat water, volume is constant. So QV, we can write QV because volume is constant according to previous old concept. That means when you heat water, internal energy of the water increase. There is no change in volume. Increase. Internal energy increase. Volume remains as such. I think it's clear. So according to previous concept, old concept, all the process in the universe occurs at constant volume. That means when you heat water, before heating and after heating, volume of water remains same. But we know that it's not true, because when you heat water, water will evaporate to form water vapor, so that volume decreases. So there is a change in volume. So old concept was wrong. Now if it were true, if that concept was true, then W will be equal to P external into delta V, work will be equal to 0. So there is no work. It indicates, according to previous concept, there is no work. But we know that it's not true. Last class we learned about two types of work, isothermal, reversible work and irreversible work. Okay, so this concept was not true. Now, if this concept was true, then work will be equal to 0, and according to first law, delta U is equal to Q plus W. Since work is equal to 0, delta U is equal to Q. Okay, I'm writing a V here because volume, constant. So when you supply heat energy, volume is constant. So that heat energy is used to increase the internal energy of water molecule. That heat energy is only used to increase the internal energy of water molecule. When you supply heat energy, that heat energy is only used to increase the internal energy. That is the meaning of all concept. But it was not true. So we are moving on to next idea, that is enthalpy. Please listen carefully. Consider a cylinder filled with HCl gas, or consider a beaker filled with water. When you heat water molecule, internal energy will increase, because by using heat energy, the internal energy, rotational energy of water molecule, vibrational energy of water molecule, translation energy of water molecule will increase, because they are absorbing energy. So that internal energy will increase. Along with internal energy, there is a change in volume. Right? There is a change in volume, because when you heat water, will evaporate to water molecule, so water vapor, so volume decreases, so there is a change in volume. Okay. Now, so all the processes in the universe are not taking place at constant volume. They take place at constant pressure. All the processes in the universe, take place at constant pressure. Because volume is changing, only pressure remains constant. When you heat water molecule, okay, volume changes, internal energy changes, but pressure before and after, external pressure remains 1 atmosphere. Before heating water, pressure will be 1 atmosphere. After heating water also, pressure of the atmosphere remains same. So actually all the processes in the universe occurs at constant pressure, not at constant volume. I think it's clear till here. All the processes in the universe take place at constant pressure, not at constant volume. Now, to explain enthalpy, consider a cylinder filled with HCl gas. Let the internal energy of this HCl gas, I am drawing once more. So consider a cylinder filled with HCl gas. Let the internal energy of this HCl gas be U1. Okay. Now let the volume be V1. Now I'm supplying heat energy at constant pressure, because all the processes in the universe take place at constant pressure. That means when I supply heat energy, that heat energy is supplying at constant pressure. Okay. So when we supply heat energy, what happens? The volume will change. By absorbing heat energy, the piston may move upwards, I don't know. Anyway, suppose if the piston move upwards, by absorbing heat energy, the piston may move upwards. So let the new volume be V2. And when HCl molecule absorb heat energy, their rotational, vibrational and translation motion increases. So internal energy increases to U2. I think it's clear. So when we supply heat energy, all the processes in the universe take place at constant pressure. So when we supply heat energy at constant pressure, QP, that heat energy is used to increase the internal energy. So internal energy of molecule increases to U2 and the volume will changes to V2. I think it's clear till here. Volume will changes. Now, you know that in our previous classes we discussed that if there is a change in volume, then the system will have a work, or there is a work energy will be formed there. If there is a change in volume, then we can observe work energy there. Okay, when there is a change in volume, here there is a change in volume. Do you remember our previous classes regarding work? When the piston move upwards, then that is expansion work. When the piston move downwards, that is compression work, which we have already discussed in our previous classes. So here, by heat energy, the piston is moving upwards. That means we can see a work energy here. We can see a work energy here. So here total energy is U1 plus PV1. This is the total energy in this system before supplying heat energy. Before supplying heat energy, V1 is the volume and P is the pressure, U1 is the internal energy. So internal energy is U plus PV1 is the pressure volume energy, that is work energy in this system. When we supply heat energy, piston move upwards, so there is work energy changes. Let the internal energy be U2. New internal energy is U2 and work energy is PV2. External pressure is P, pressure remains constant, new volume is V2. I think it's clear. Here volume V1 volume is changes to V2 volume. That means there is a work energy. You can observe a work energy here. When the piston move upwards or downwards, upwards expansion work, downwards compression work. So you can observe a work energy. So here before adding heat, let U1 be the internal energy and due to V1 volume, PV1 be the work energy. When we supply heat energy, internal energy increases to U2 and volume changes to V2. So U1 is the internal energy plus here work energy is PV2. Work equation is minus P external into delta V. Neglecting that minus, okay, PV2. I think it's clear till here. Now, so we can write that by supplying heat energy, QP, internal energy changes to supplying heat energy, internally changes to U2 and pressure volume energy changes to PV2. Okay. Internal energy changes to U2 and pressure volume energy changes to PV2. So QP is equal to U2 plus PV2 minus U1 plus PV1, because here U1 plus PV1 is changes to U2 plus PV2 when we supply heat energy. When we supply heat energy, in sum of internal energy and pressure volume energy, U1 plus PV1 in the system changes to U2 internal energy plus PV2 work energy. So heat QP is equal to U2 plus PV2. This energy minus this energy. I think it's clear. Here total energy is U1 plus PV1. Internal energy and work energy is PV1. This is internal energy and this is work energy. So sum of internal energy and work energy is U1 plus PV1 in this system. When we supply heat energy, internal energy changes to U2 and volume changes to V2. So here internal energy plus pressure volume energy, that is work energy, is U2 plus PV2. So we can write QP is equal to heat supply is equal to U2 plus PV2 minus U1 plus PV1. I think it's clear. Now, enthalpy. What is enthalpy? Enthalpy means actually it is the ENTHALPY, enthalpy. Enthalpy is the, actually it is the total heat content of the system H. It is the sum of internal energy and pressure volume energy. It is the sum of internal energy and pressure volume energy. Sum of internal energy and pressure volume energy is known as enthalpy. Actually, sum of internal energy and pressure volume energy is actually enthalpy. It is defined like this, total heat content of the system. But actually, it is the sum of internal energy and pressure volume energy of the system. If you consider this bottle is filled with water. This bottle is having an internal energy and this bottle is having volume till here. So this is having a work energy. Sum of internal energy and pressure volume energy or work energy is known as enthalpy. It is the sum of internal energy and pressure volume energy. So QP is equal to, what is U2 plus PV2? U plus PV is H. So what is U2 plus PV2? H2. What is U1 plus PV1? H1. So what is QP? QP is equal to delta H. So QP is equal to delta H. Okay. U2 plus PV2. U plus PV is H. So U2 plus PV2 is H2 minus U1 plus PV1 is H1. So H2 minus H1 is delta H. Or we can write like this. Or we can write like this. Instead of QP, you can write delta H. So delta H is equal to, instead of QP, you can write delta H. Delta H is equal to U2 plus PV2 minus U1 was PV1. Okay, I am expanding this equation. U2 plus PV2 minus U1 plus PV1. Right. Okay, now delta H is equal, I am taking U terms. So U2 minus U1, U2 minus U1 minus U1 minus PV1. U2 minus U1 plus P into V2 minus V1. I am taking P outside from these two. P into V2 minus V1. That is delta H is equal to U2 minus U1 delta U plus P into V2 minus V1 delta V. So these are the two equations to calculate enthalpy. These are the two equations to calculate enthalpy. Okay. So what is enthalpy? It is the total heat content of a system. Defined as, enthalpy is defined as, it is the total heat content of a system, but actually enthalpy is the sum of internal energy and pressure volume energy inside a system. It is actually the sum of internal energy and pressure volume energy of a system. I think it's clear. If you consider this as the system, this water molecule will possess internal energy less the internal energy plus be U, and due to its volume, it is due to it has some volume. So due to that volume, at constant pressure, it possesses a work. So sum of internal energy and work, pressure, volume, work energy is known as enthalpy. And enthalpy change of a system, when you supply heat energy, internal energy changes to U1 to U2, enthalpy volume changes from V1 to V2. At that time, you can calculate enthalpy by using two equations. QP is equal to delta H, or QP delta H is equal to delta U plus P delta V, because QP is delta H. Substituting this delta H in this equation, so delta H is equal to U2 plus PV2. Okay, substituting, we will get delta H is equal to delta U plus P delta V. These are the equations to calculate change in enthalpy. Change in enthalpy. So change in enthalpy is equal to change in internal energy plus pressure into change in volume, or change in enthalpy is equal to heat at constant pressure. Heat at constant pressure. I think it's clear. It is one of the important topic in thermodynamics. So enthalpy is the total heat content of a system. It is the total heat. It is the total heat content of a system. It is calculated by adding internal energy of the system plus, due to volume, there is pressure volume energy, that is work. Pressure volume energy. Sum of these two is known as enthalpy, or total heat content. Enthalpy is known as total heat content. I think it's clear. Moving on to next topic. Hi dear students. Moving on to next topic, relationship between delta H and delta U. Now what is the relationship between delta H and delta U? What is delta H? Change in enthalpy. And what is delta U? Change in internal energy. So we have to derive relationship between delta H and delta U. Last class when we discussed about enthalpy, we derive an equation relating delta H and delta U. What is that relation? Delta H is equal to delta U plus P delta V. Okay, we have already derived this relation, and this relation, this is the relationship between, there is a relationship between delta H and delta U. Okay, this equation contains delta H and delta U. So this is the first equation relating delta H and delta U. We already derived this equation. Now we are going to derive one more equation. Now consider an ideal gas filled in a system. Let the internal energy be U1, its volume be V1. Okay, now suppose what is internal energy, pressure, volume, energy? If pressure is constant, always reaction occurs at constant pressure. Okay, all these topics we discussed in our previous class. So let the pressure be P, pressure is constant. So internal energy plus pressure volume energy, internal energy plus pressure volume energy is enthalpy. So let the enthalpy of this system be H1. Now if the system absorbs heat energy, okay, the internal energy and volume changes to U2 and PV2. So let the new enthalpy be H2. So what is change in enthalpy? Delta H, H2 minus H1, that is H2 is U2 plus PV2 and H1 is U1 plus PV1, right? From this relation we derive this equation. So this is the first equation relating delta H and delta U. Delta H is equal to delta U plus P delta V. This is the first relation, this is the first equation relating delta H and delta U. We already know this equation, we already derived this equation in our previous class. So moving on to next equation, second equation. So first equation relating delta H and delta U is delta H is equal to delta U plus P delta V. This is the first equation. Moving on to second equation. Now we know that delta H is equal to delta U plus P delta V. Now for ideal gas, what is the ideal gas equation? For ideal gas, PV is equal to nRT. Okay, so change in pressure volume is equal to change in nRT, right? Change in pressure, if you take change of pressure and volume, change in pressure volume is equal to change of nRT, right? Now we know that all our process occurs at constant pressure. So here pressure is constant, so I am taking P outside this delta because pressure is not changing, pressure remains constant. There is no change in pressure. All our reaction occurs at constant pressure. Last class we discussed about those details. So all the process occurs at constant pressure. So I am taking P outside. So P into change in volume. There is a change in volume. V1 changes to V2. You can observe that change is equal to delta of nRT. I think it's clear. Delta of nRT. Okay. Now delta of nRT. Now we know that R is constant. Now suppose this reaction occurs at constant temperature. At constant temperature delta T. Okay, there is no change in temperature. Delta T is equal to 0. If this process occurs at constant temperature, then T is constant. R is universal gas constant. R is always constant. So you can take R outside delta because R is constant. And T is temperature. I am taking temperature as constant. So at constant temperature, you can write P delta V is equal to delta N and R and T. Delta is only for N. Delta N. Here R constant, T constant. So P delta V is equal to delta nRT. Okay. Now what is the relation between delta H and delta U? Delta H is equal to delta U plus P delta V. So instead of P delta V, we can write delta nRT. Okay. So delta H is equal to delta U plus delta nRT. Delta U plus delta nRT. Delta U plus delta nRT. Okay, so delta H is equal to delta U plus delta nRT. Instead of PV, I am taking P delta V, I am taking delta nRT because for ideal gas, P delta V is equal to delta nRT. Okay, now what is delta N? Delta N is change in number of moles. Or accurately you can name it as delta Ng. Actually it is delta Ng. G stands for gas. So delta Ng. This is the correct form of writing this equation. Delta H is equal to delta U plus delta NGRT, because we are considering gas. Because we are considering gas, for ideal gas PV is equal to nRT. We are considering gas, that's why PV will become, or PV become equal to nRT. If it is solid or liquid, you cannot take this equation, because this equation is only for ideal gas. You cannot use solid, or for solid or liquid you cannot use this equation, because here for PV I am substituting nRT, and this is possible only for gas, ideal gas. So PV is equal to nRT, so P delta V is equal to delta nRT, and this equation is only used for gas, so let it be delta Ng, gas. G indicate gas. So delta Ng, change in number of moles in gaseous state. Change in number of moles in gaseous state. Okay, so this is calculated using this equation. Number of moles of products in gaseous state minus number of moles of reactants in gaseous state. Delta Ng means number of moles of products in gaseous state minus number of moles of reactants in gaseous state. So these are the two equations relating delta H and delta U. This equation we have already discussed when we discussed enthalpy. And second equation, delta H is equal to delta U plus delta NGRT. This equation is used only for gases. This equation is used only for gases, because instead of PV we are writing nRT, and this is possible only in the case of ideal gas, because PV is equal to nRT. So this equation is used only for gases. Delta H is equal to delta U plus delta NGRT. These are the two equations relating delta H and delta U. I think it's clear. Now, what is delta Ng? Delta Ng means number of moles of products in gaseous state. Let this be the product. So number of moles of product in the in gaseous state minus number of moles of reactants in gaseous state. Suppose consider this equation. Consider this equation. Consider this equation. N2 gas plus 3H2 gas giving 2NH3 gas. Here N2 and H2 are reactants. And this ammonia is our product. Right? So what is delta Ng? Number of moles of products. Number of moles of products in gaseous state. Ammonia is also exists in gaseous state. Number of moles of products in gaseous state minus number of moles of reactants in gaseous state. So in gaseous state, number of moles of products. Here delta Ng is equal to number of moles of products. This one is product and this is present in gaseous state. Number of moles 2. 2 minus these two are reactant. They exist in gaseous state. Number of moles 3 plus 1 4. So what is delta N? Minus 2. Right? Delta N is minus 2. So substituting this value here, delta H is equal to delta U minus delta Ng is minus 2. So minus 2 RT. Okay. So this is the relationship between delta H and delta U. These are the relationship between delta H and delta U. I think it's clear. Moving on to next topic, equations to calculate delta U and delta H. Now, I think we have derived 2 equations for delta U and 3 equations for delta H. So we have to recollect those equations. So we have derived 2 equations for delta U and 3 equations for delta H. Equations for delta U are delta U is equal to Q plus W. First law of thermodynamics, mathematical statement of first law of thermodynamics. Thermodynamics. Right? dynamics. Okay, dynamics. So this is the first equation we discussed, and this equation is used to calculate delta U. So this is the first equation for delta U. And second equation for delta U is equal to QV. That is delta U is equal to QV. When volume is equal to, I don't know if you remember, what is W minus P external into delta V. Now if volume is constant, at constant volume delta V is equal to 0. This will become equal to 0. So W is equal to, right, W is equal to 0. When W become equal to 0, you will get delta U is equal to Q. Delta V. At constant volume, delta V is equal to 0. So this will be equal to 0. So minus P externally to 0, W will get 0, right? Right. So at a constant volume, I think you remember this one, this equation. At a constant volume, delta V is equal to 0. So W, what is W? Minus P external into delta V. So W will be equal to 0. So substituting this value, W is 0, you will get delta U is equal to Q. I am writing a V here. This indicates heat at constant volume. Volume is constant. So we have derived these two equations. Right? Now, equation to calculate delta H. Now for delta H, we discussed nearly 3 equations. First equation, delta H is equal to QP. Heat at constant pressure. Heat at constant pressure. We derived this equation when we were discussing about enthalpy. Here delta U is equal to heat at constant volume. Right. Now second equation, delta H is equal to delta U plus P delta V. And we discussed this equation when we discussed about relationship between delta H and delta U. Now last and final equation, delta H is equal to delta U plus delta NCERT, and this equation is used when reactants and products, or if there is if reactant or products are gases. Okay, this equation is used either reactant or product or both are gases. This equation is used only for gases. So these are the 3 relations. These are the 3 equations to calculate delta H, and these are the 2 equations to calculate delta U. I think it's clear. Moving on to next topic, heat capacity, specific heat capacity and molar heat capacity. So moving on to next topic, heat capacity, specific heat capacity, molar heat capacity. Heat capacity is represented by capital C. Specific heat capacity, and this one is represented by small c. And molar heat capacity is represented by C, M. Capital C and M. M as subscript. Capital C and M as subscript. You have to write M as subscript. So we are going to discuss about heat capacity C, capital C, specific heat capacity small c, and molar heat capacity Cm. Now what is heat capacity? Heat capacity means it is the heat required to raise temperature of a substance by 1 degree Celsius. Consider a substance. Let this be the substance. So heat required to raise temperature of the substance by 1 degree Celsius. That is heat capacity. If you consider a cup of water, if you consider a cup filled with water, and let the temperature of this cup be 26 degrees Celsius. Okay, to make this 26 degrees Celsius to increase this 26 degrees Celsius to 27 degrees Celsius, we have to supply heat energy, right? So to increase the temperature of this water, okay, by 1 degree Celsius, we have to supply heat energy. So heat required to raise the temperature of a substance by 1 degree Celsius. That heat is known as heat capacity. Heat required to raise temperature of a substance. Let the temperature of the substance be 26 degree, and when we supply heat energy, temperature will increase from 26, okay, to 27. When we supply heat energy, temperature will increase, and the heat required to raise temperature of the substance by 1 degree Celsius, that is known as heat capacity. Okay, it is the heat required to raise temperature of a substance by 1 degree Celsius. Now, so change in temperature directly proportional to heat supplied. Change in temperature. So there is a change in temperature, 26 degree changes to 27 degrees Celsius. So change in temperature directly proportional to heat supplied. So change in temperature directly proportional to heat supplied. Okay, I think it's clear. So change in temperature is directly proportional to heat supplied. Or you can write like this. Q is directly proportional to delta T. Okay. Q is directly proportional to delta T. Anyway, you can write like this. I think it's clear. So change in temperature directly proportional to heat supplied. Okay. So Q directly proportional to delta T, heat supplied directly proportional to change in temperature. So Q is equal to, so this proportionality is removed by multiplying with a constant, let the constant be C, heat capacity. C into delta T. Okay. So what is C? C is equal to Q by delta T. This is the equation to calculate heat capacity. C is equal to Q by delta T. This is the equation to calculate heat capacity. What is heat capacity? It is the heat required to raise the temperature of a substance by 1 degree Celsius. If consider a cup filled with water, let the temperature of the cup be 26 degrees Celsius. So heat energy required to raise temperature of this cup from 26 to 27. That is known as heat capacity. And the formula to calculate heat capacity is C is equal to Q by delta T. Okay, I think it's clear. Moving on to second one, that is specific heat capacity. Now what is specific heat capacity? Heat required to raise, same way, heat required to raise temperature of a substance. Heat required to raise temperature of unit mass. Unit mass means 1 kilogram. So here weight of substance is specified. Here we are not specifying the weight of substance. We are taking some substance with, you can consider any weight. But here in specific heat capacity we are considering a substance of unit weight or unit mass. So heat required to raise temperature of unit mass of substance by 1 degree Celsius. So here we are specifying the mass of the substance. So consider a substance. Mass of substance is 1 kg and here temperature of the substance be 26 degrees Celsius. So heat required to raise temperature of 1 kilogram substance by 1 degree Celsius. So we have to increase temperature of 1 kg of substance from 26 to 27, that is 1 degree Celsius. We have to increase the temperature by 1 degree Celsius. So heat required to raise temperature of 1 kilogram, that is known as the unit mass, 1 kilogram of substance by 1 degree Celsius. That is known as specific heat capacity. And specific heat capacity is calculated using this formula. Small letter c, small c is equal to Q by M into delta T. This is the equation to calculate specific heat capacity, Q by M into delta T. Q divided by M delta T. M means mass. Delta T means change in temperature. Change in temperature. So Q, C is heat capacity, Q heat and delta T change in temperature. Here C heat capacity, Q heat supplied or heat absorbed and delta T change in temperature. Here C is equal to Q by M into delta T. We have to divide with mass. So C specific heat capacity, M heat absorbed, M mass and delta T change in temperature. I think it's clear. Now molar heat capacity. What is molar heat capacity? If specific heat capacity means it is the heat required to raise temperature of 1 kilogram of substance by 1 degree Celsius. So what is molar heat capacity? It is the heat required to raise temperature of 1 mole. 1 mole. We are considering 1 mole of substance. Here we are not specifying the mass of the substance. Here we are specifying the mass and it is taken as 1 kg. And here also we are specifying the amount. Here the amount is 1 mole. So heat required to raise temperature of 1 mole substance to 1 degree Celsius. It is the heat required to raise temperature of 1 mole of substance. Okay, 1 mole of substance by 1 degree. Okay, so it is represented by Cm is equal to Q by N into delta T. Cm means molar heat capacity, N number of moles. Q heat absorbed, delta T change in temperature. So these are the 3 important topics. First one is heat capacity. It is the heat required to raise temperature of a substance by 1 degree Celsius. Formula C is equal to Q by delta T. Now second one, specific heat capacity. Heat required to raise temperature of unit mass of substance by 1 degree Celsius. Heat required to raise temperature of unit mass, that is 1 kilogram of substance by 1 degree Celsius. So small c is equal to Q by m into delta T. M means mass, delta T change in temperature, Q means heat. Now third one, molar heat capacity. Heat required to raise temperature of 1 mole. We are considering 1 mole of substance. So heat required to raise temperature of 1 mole of substance 1 degree Celsius. Formula Cm is equal to Q by n into delta T. N means number of moles. I think it's clear. Moving on to next topic, heat capacity at constant pressure and heat capacity at constant volume. Now what is heat capacity? Heat capacity is C. Formula C is equal to Q by delta T. Right. Now heat capacity at constant pressure. So heat capacity is C. Now at constant pressure you can write it as Cp. Since pressure is constant, you can write that pressure as subscript. So heat capacity Cp. Cp means heat capacity at constant pressure. Okay, now we know that C is equal to Q by delta T. Heat capacity is equal to Q by delta T. Now at constant pressure, C will become Cp. At constant pressure, heat capacity will change us to Cp, heat capacity at constant pressure. Since pressure is constant, C, heat capacity will change us to Cp. Now Q will change us to Qp. So C will change us to Cp and Q will change us to Qp at constant pressure. So you can write like this: Cp is equal to Qp by delta T. Right? Now we already discussed that. What is Qp? Qp means it is delta H. Right? Qp means it's delta H. Heat at constant pressure is delta H. Okay, if you check previous classes or previous topic, you can see that we have written this equation: delta H is equal to Qp. Heat at constant pressure is known as enthalpy change, delta H. We discussed about, or we learned 3 equations for delta H. Delta H is equal to Qp, delta H is equal to delta U plus P delta V, and delta H is equal to delta U plus delta NCERT. Right? One of the equation is delta H is equal to Qp. So instead of Qp I am writing delta H. So equation will become Cp is equal to delta H by delta T, or you can write delta H is equal to Cp into delta T. So fourth equation for delta H. Delta H is equal to heat capacity at constant pressure into change in temperature. So already we learned 3 equations. Delta H is equal to Qp, delta H is equal to delta U plus P delta V, delta H is equal to delta U plus delta NCERT. Fourth equation for delta H is equal to Cp into delta T. I think it's clear. Once more, heat capacity at constant pressure means Cp. Heat capacity. What is heat capacity? Heat required to raise temperature of substance by 1 degree Celsius. Now, equation to calculate heat capacity is C is equal to Q by delta T. At constant temperature, C changes to Cp, Q changes to Qp, so that Cp is equal to Qp by delta T. Right? Now, what is Qp? It is delta H. So Cp is equal to delta H by delta T. So delta H is equal to Cp into delta T. So fourth equation to calculate enthalpy change. Enthalpy change is equal to heat capacity at constant pressure into change in temperature. Okay. Moving on to next one, heat capacity at constant volume. What is heat capacity at constant volume? It is heat capacity C, constant volume means you have to write V as subscript, Cv. So heat capacity at constant volume, Cv. Okay, Cv. Now equation for heat capacity, C is equal to Q by delta T. Now at a constant volume, C changes to Cv and Q changes to Qv, right? At constant volume, C changes to Cv and Q changes to Qv. Okay, I think it's clear. So you can write like this: Cv, instead of C, you can write Cv is equal to Qv divided by delta T. Cv is equal to Qv divided by delta T. Right? Now, what is Qv? What is Qv? Qv means it is delta U. We learned 2 equations to calculate delta U. One is delta U is equal to Qv. Second equation is delta U is equal to Q plus W. First law of thermodynamics. So delta U is QV. So instead of QV, you can write delta U here. So you'll get CV is equal to delta U by delta T, right? So what is delta U? Delta U is equal to CV into delta T. So delta U is equal to CV into delta T, right? CV into delta T. So we can write, okay, delta U is equal to CV into delta T. So this is the third equation to calculate delta U. So we have already learned two equations. Delta U is equal to QV, delta U is equal to Q plus W, and third equation delta U is equal to CV into delta T. Change in internal energy is equal to heat capacity at constant volume into change in temperature. I think it's clear. CP and CV, heat capacity at constant pressure and heat capacity at constant volume. I think it's clear. Moving on to next topic. Relationship between CP and CV. Heat capacity at constant pressure and heat capacity at constant volume. So next topic, relationship between CP and CV. Heat capacity at constant pressure and heat capacity at constant volume. Consider ideal gas. Consider a system filled with ideal gas. Consider a system filled with ideal gas. Let the number of moles. Let number of moles N be 1. Let the number of moles be 1. Let the number of moles of ideal gas be 1. Now, we know the equation to calculate delta H. Delta H is equal to delta U plus, since this is gas, we can write delta Ng RT, right? Delta Ng RT, right? Now, delta H is equal to delta U plus delta Ng RT. Now, if for 1 mole, you can write like this, delta H is equal to delta U plus delta of, or R into delta T, or delta of RT. Delta of RT, because here N is 1. Okay, here the number of moles be 1. So, you can write N as 1. So, delta H is equal to delta U plus delta RT. Okay. So, delta H is equal to, since R is a constant value, you can take this R outside this delta. So, you will get delta U plus R into delta T. Okay. Here we are not considering temperature as constant. Here we are not considering temperature as constant. Please listen to that point. We are not considering isothermal condition. We are not considering temperature as constant. So temperature is not constant. There is a change in temperature. So according to this equation, delta H is equal to delta U plus delta Ng RT. Here we are considering only 1 mole. So let the N be 1. So delta H is equal to delta U and delta RT plus delta RT. R is constant, I'm taking this R outside, so we'll get delta H is equal to delta U plus R delta T. Okay, now what is the relationship between delta H and heat capacity at constant pressure? Delta H is equal to Cp delta T. Now what is the relationship between delta U and Cv? We know that delta U is equal to Cv delta T. We know this equation, right? So I'm substituting Cp delta T instead of delta H, because delta H is Cp delta T. So I'm writing here Cp delta T is equal to, instead of delta U, what is delta U? Cv delta T. So Cv delta T plus R delta T. Okay. Dividing this equation by delta T, you will get Cp is equal to Cv plus R. When we divide the whole equation with delta T, these two delta T will cancel, these two delta T will cancel, these two delta T will cancel. That means all delta T will cancel. You will get Cp is equal to Cv plus R. Okay. So Cp is equal to Cv plus R, or I am taking the Cv this side. So you will get Cp minus Cv is equal to R. Heat capacity at constant pressure minus heat capacity at constant volume is universal gas constant. This is the relationship between Cp and Cv. This is the relationship between Cp and Cv. I think it's clear. So consider a system filled with ideal gas. Let the number of moles in the system be 1. Let the number of moles be 1. So according to this equation, that is delta H is equal to delta U plus delta Ng RT. Here N is equal to 1. So delta H is equal to delta U plus delta RT. Now I'm taking R outside this delta because R is constant. There is no change in R. So I'm taking R outside. So delta H is equal to delta U plus R delta T. Here we are not considering temperature as constant. Here we are not considering temperature as constant. So temperature is not constant, there is a change in temperature, delta T. So what is delta H? Cp delta T. Because we are going to derive an equation for Cp and Cv. So instead of delta H you can write Cp delta T. Instead of delta U you can write Cv delta T plus R delta T. Dividing with R delta T you will get Cp is equal to Cv plus R. I'm taking Cv this side, so Cp minus Cv is equal to R. This is the relationship between Cp and Cv. I think it's clear.